like SERA, a European project with funding from the European Commission that ran for a number of years. The output of this model was not just a map, it wasn't just a single product, a single PGA map, but it was really an extensive set of data sets and models which users can access and reproduce the calculations of seismic hazard. So we have the European earthquake catalogues, we have an active fault database, we have data on strong motion across Europe, models for estimating strong ground motion, and all of these have been released on this platform which is called EFER, European Facilities for Earthquake Hazard and Risk. So that website there, that link there, you can go and download each of the components that were released to create this seismic hazard model, and this allows for reproducibility of the model. The calculations were carried out with the OpenQuake engine, so you can insert the input into the OpenQuake engine and rerun the calculations. But if you're, as Vito was mentioning, if you're not interested in actually running and checking calculations, but you just want the outputs of the hazard model, this platform also provides pre-computed seismic hazard outputs. So if you go to this hazard interface on this platform, you can access maps. You can choose to see the spatial distribution across the whole of Europe of spectral acceleration on a reference bedrock for different periods of vibration, so from what is basically PGA up until a spectral acceleration at 4 seconds. And you can look at these results for different return periods, from 73 years up to almost 5,000 year return period. And so you can download the data, you can download the map, you can click on a specific location and get the uniform hazard spectra from all of those outputs that are there. So in the SERA project, that European seismic hazard model is being updated. So updates are being carried out to both the historical and the instrumental earthquake catalogues across Europe. There have been earthquakes since 2013 across Europe, but there's also been a lot of research to look back at historical earthquakes which were missing from the historical catalogues at the time of the SHARE project. Again, the active fault database has been enriched through contributions from various geotechnical engineers across Europe. And the logic tree is being put together of the source zones describing the areas where earthquakes can occur in Europe and the ground motion models. But all of this is being done, as for SHARE, for a reference bedrock. So for what we call a VS30, so that's the average shear wave velocity over the top 30 meters of soil of around 800 meters per second. All of this, again, will be released on the EFER platform in April next year. And at the same time, we will also be releasing the European risk model, as I mentioned earlier. However, as I also described earlier on, and as was a question posed to Vito, how are we going to get the ground motion at the surface? The European seismic hazard model provides us with the levels of ground shaking on bedrock, but our buildings are located on soils with different properties. How are we going to include that site amplification, those amplified strong ground shaking that's going to occur under our buildings? So to do this, we need, for the whole of Europe, a site amplification model. So as was mentioned earlier, there are traditional models that use proxies that relate the slope, the topography of the land to VS30. So where we have measurements of that average shear wave velocity over the top 30 meters, we have a number of places across Europe where we know the value of VS30. We can plot it against what is the slope at that location. And there's a certain correlation, but as you can see, there's a lot of uncertainty in that relationship. But if we take that relationship between slope and VS30, we have a model of the topography across the whole of Europe, and we can put together a model of VS30 and how it varies across the whole of Europe. But it's not just the slope that influences site amplification. Geology is also known to have a large impact on levels of ground shaking and site amplification. So within the SERA project, our colleagues at BRGM in France, who have worked in a number of different European projects, one is the ProMine project, and One Geology is another project that has put together geological maps of different countries. They have harmonized all of this at a European scale. So we now have harmonized geological maps at the European scale. There was a work carried out in Portugal by Villanova et al. That proposed a correlation between geology and VS30. So using those geological maps, the different geological units, we can then estimate the VS30, and again we have a way to produce a map for the whole of Europe of estimates of VS30. So what we do with those is that we put them within our traditional ground motion prediction equations. So this is an equation which tells us the level of ground shaking. It's a function of the magnitude, of the distance to the event. It could also be a function of the style of faulting. But it's also a function of the site, and there's obviously also some aleatory variability. So typically this site function is a function of VS30. So once we know the VS30, we can plug it into our ground motion model and get an estimate of the ground shaking for that location with that value of VS30. But what we're doing within SERA is to try and replace this part of the ground motion model, this site model, not with VS30, but to put directly in the slope and the geology, and to use those terms as input into our ground motion model. This has been possible thanks to a database called the Engineering Strong Motion Database. It's a database of recordings at many sites across Europe. Many of those sites have repeated recordings, and so a new European ground motion model is being developed for Europe using the data from this database. And so this site amplification term will no longer read VS30 as an input parameter, but slope and geology as the input parameters. So the equation, I didn't notice this earlier, but the equation has gone a little bit strange, but this is just the function of the slope and the topography. So here we have different values of slope for different geological units, and we can look at the correlation between slope, geological unit, and this site term which goes into the ground motion model. So for a given, so this map here shows for a given assumed slope and geological unit, this would be how the site amplification term in the ground motion model varies across Europe. So we can produce those maps for different slope values and different geological units. I just wanted to spend a few words on the Engineering Strong Motion database. You may not be familiar with this. This is a quite recent database that's been released. This is the link to the website. And it includes strong ground motion recordings from European, Mediterranean, but also Middle Eastern earthquakes. And you can download those recordings from the website. It has a feature which is called Repsol Lite, which is a tool for selecting records to be compatible with a given response spectrum as well. So this is quite useful for structural engineers that need ground motion recordings for nonlinear dynamic analysis of structures. They can come to this website and obtain the ground motion recordings. So that was my update on where we are with seismic hazard, and as I say, in a year's time there will be an update to that European seismic hazard model, and also a way of introducing site amplification into the hazard. So a few words on building exposure and how we're developing a European exposure model. So towards the end of last year, we released what we're calling the V0.1 European exposure model. This was actually used within the global earthquake model seismic risk map that Vita presented earlier. So that global seismic risk map for the whole of the world, the European component of it was using an exposure model that we had developed within SERA. But it was a very early version, as I say, version 0.1, and we continue to improve this exposure model. This model describes the spatial distribution of residential, commercial, and industrial building classes, and it tells us what is the number of buildings, what's the replacement cost of those buildings, and what are the people, what's the number of the people within those buildings. As was presented earlier today, we're using the GEM building taxonomy to classify the buildings in every single country in Europe. There are a number of attributes of the GEM building taxonomy. I think Vita showed 13 earlier, but we've selected just a small number that we're using to describe building classes in every single country. So we're using the main construction material. This could be cast-in-place reinforced concrete, could be pre-cast concrete, unreinforced masonry, could be reinforced masonry, confined masonry, adobe steel, and so on, timber. We describe the lateral load resisting system. Is it an infilled frame? Is it a wall or a dual wall frame system? Or is it more of a post and beam where there's not really a moment frame system? The number of stories is important as well. The seismic design code level is something that we're assigning to the buildings. Are the buildings, were they constructed before any seismic design code was introduced in the country? Were they constructed when there was a low code, the first time that seismic design was introduced in the country, but perhaps an allowable stress method was being used, just a certain percentage of the weight is being applied as a lateral force to design the building. Then to more moderate codes where ultimate limit state approaches are used, ductility starts to be considered, up until very modern high code, Eurocode 8 type with capacity design, ductility requirements, and so on. And then, in addition to assigning what type of code has been used at the time, the lateral load coefficient used in the seismic design can also be assigned. I'll go through in a moment a slide showing how we calculate that. So here are just some examples of building classes within our European exposure model and showing what the GEM taxonomy looks like. Here are some unreinforced masonry residential buildings, some reinforced concrete frame buildings. These are the residential classes. Up here, some typical industrial steel or precast post and beam or frame buildings. Some commercial buildings used for retail or also used for hotels and offices, typically also in reinforced concrete buildings. So how are we putting together this European exposure model? We are collecting lots and lots of publicly available data from all across Europe. We have a spreadsheet which is available to download, which gives the sources for each country where we found data on buildings. We have the national census data in each country. We also have, there's been other projects called Tabula, somewhere down here, I don't know if you can see it, but there's a Tabula project which looked at the energy efficiency of buildings. There's an EU buildings database. There's a number of sources of data that have allowed us to identify what are the number of buildings in the country, or what are the number of dwellings within the country. What is the area and the cost, and how are they spatially distributed within the country? Once we have put together all of those various sources of data and we have an idea of the number, the spatial distribution, their value, we then need to distribute that between different building classes. Different building classes according to the GEM building taxonomy. So this is an example, I can't remember which country this is, Venetia probably knows from looking at it by heart, but I took it from one of her slides. But this is showing a distribution of the residential buildings across those different building classes within one of the countries in the Balkans. How do we get this distribution? This distribution, the information in these building classes is not available typically from those national publicly available sources of data. The census does not tell us the percentage of reinforced concrete frame buildings with infills of 3 stories. They might tell us the percentage of buildings of 3 stories. They might tell us the percentage of buildings built before 1960, or with concrete as an external material, or with unreinforced masonry as an external material, but we don't know for sure that masonry is the lateral load resisting system in that case. So we need to develop this distribution of building classes through a number of different ways. So one is through expert judgment. So we have, many of you came to a workshop in Pavia, on the exposure workshop, where we asked you to help us fill in a questionnaire to describe what is the distribution of building classes. What are the main building classes that you use in your country to construct residential buildings or industrial or commercial buildings? How are they distributed? What is the predominant building class in urban areas as opposed to in rural areas? How do they differ between urban and rural areas? We have other projects, as I mentioned, in particular for industrial buildings, have looked at the distribution of industrial buildings across Europe. Peer-reviewed publications, a number of publications have produced risk models for countries across Europe and have described the building types within those countries for the risk models. We can look at satellite imagery, we can use Google Street View, especially for commercial buildings. We can go into some cities and we can actually try and get a feel for what the main key building types are. For residential buildings, we can use what we call mapping schemes. So we don't need to ask directly to the experts, what's the distribution of buildings in your country, but we can ask for a building of a given year, a given era, that has a given external material and a given number of stories, what is the most likely building class? What is the most likely lateral load resisting system that has been used to construct that building? And as I mentioned before, often the census does provide us with at least some of this information across the country. When it comes to the design code and the lateral force coefficient, we're assigning this to reinforced concrete buildings. We're not assuming that masonry buildings have been, unreinforced masonry buildings have been designed, but that the reinforced concrete buildings in the countries have been designed to those different codes that I mentioned. And so by doing a study on the evolution of seismic design codes within each country, we can get an idea at a given time period, what was the code that was being used, and within the country, what was the level of seismic design that was requested. Again, this is something that we've contacted some of you about, and we're getting feedback from people all across Europe helping us to identify those seismic design codes, translate them in some cases, and put together here what you see is for different countries in Europe, what was the year at which seismic design was first introduced, for how long did you have this more low code approach, when was it upgraded to a moderate code, and when did Eurocode 8 style a code get introduced into the country. So in order to assign then a lateral force coefficient, so it's not just the fact that a code was introduced at a given time. So if I take any one of these countries and I take a given year, not all of the buildings in the country would have been designed with that code, because some areas of the countries have been classified as seismic zones, some areas are not, or they're classified with different levels of seismic design. So here in the maps here you see an example of Italy, where from around 1915 there was the requirement to seismically design buildings, but just in those areas that you see which are in red. So we want to digitize these maps so that when we have in our exposure models buildings from 1915 in those areas, we can say that they were seismically designed. We can also calculate the value of lateral force that was specified in the code. Most codes across Europe identified up to 4 different parameters that needed to be calculated. So one is the seismic coefficient, which varies as a function of the zone of the location of the building. There may be, in some cases, a structural coefficient taking into account the ductility. Is it a steel building or a reinforced concrete building? Is it a frame or a dual building? A dynamic coefficient, which was starting to bring in the spectral shape and the impact of the soil. And importance coefficient, though this is typically 1 for the buildings that we're considering here, these residential commercial buildings. So everything that we are developing in terms of the European exposure model is being made, and will continue to be made publicly available through this platform, which is the European Seismic Risk Service. It is part of the AFAIR group of services. So AFAIR I mentioned earlier, where you can find the hazard data. This is the equivalent for the risk data. So we already have a page on exposure there, where we have the spreadsheet I showed you earlier with the sources of where we're getting building data across Europe. We have some documents, some deliverables, which explain how we're developing this European exposure model. And then we have these 3 interactive viewers, where you can go and view the data through a web-based GIS. So this is one example of one of the interactive viewers, which shows how the number of buildings, or the population, or the replacement cost, you can choose, is spatially distributed on a grid throughout Europe. And then you have a legend showing obviously what those numbers mean. Another interactive viewer that we are experimenting with is showing for the whole country what is the total number of population or number of buildings, and then these pie charts to give an idea of how those buildings are distributed between different materials. And we're looking at other ways to bring in those other attributes, the number of stories, the lateral load resisting system. Obviously it gets quite complicated to present this information on a map at some stage. So eventually what we would plan to do is to provide CSV files, and so by clicking on a country you can then also download the CSV file of the exposure model for that country and then run calculations with the OpenQuake engine. This is just a third interactive viewer. This is at level 1, administrative level 1 boundaries of each country across Europe. As you can see, they vary quite a lot. In the UK, the administrative level 1 is basically England or Scotland or Wales, whereas here in the Balkans we have quite small administrative level 1 boundaries. So we're thinking of ways in which we can provide this information at a higher resolution, but also, as you see here, when you come onto the interactive viewer, you have all the information of attributions. Here I'll show you what happens when you click on here, the exposure contributors. I'll show you in the next slide. But you have also DOI, so everything has an identifier. There's a license, and Creative Commons open data license, an abstract, and so on. So let me skip forward. So if you click onto that contributors, you go to a page on the website which has all of the contributors, all of the people that are contributing to that exposure model from different countries across Europe. So just going back one slide, in addition to these interactive viewers, which really just allow you to see the data, to maybe download some CSV files, but not really do much with them, we also offer what are web services. So these web services allow you to bring that data into your own tools. So QGIS was shown earlier by Vita. This is just an example of QGIS. If I go to up here on the left, you can add new connection, WMS or WMTS connection. And if you just copy this link from the website and put it in to QGIS, it will bring the data from those interactive viewers into your own QGIS installation. So you can work directly with the exposure data locally. Okay, now I'm going to talk about the final component of physical seismic risk, which is physical vulnerability. We have been together with our partners in the SERA project and also with some experts that came to a workshop that was held in Portugal last year. We've been trying to develop a framework for European fragility and vulnerability functions. Now, I will show you the figure of what this looks like. It's rather complicated. I don't really have time to go through every single step of it, but I'll just point out a few of the more interesting features of this framework. So one is a database of existing fragility functions, existing capacity curves, existing vulnerability models. So these have been collected, as Victor also mentioned earlier. This has been done at the global scale. We've continued to do this at the European scale. So we have, as you see, there are over 500 different capacity curves, over 400 fragility functions that are in this database, which follows the GEM vulnerability data model so that we can put it inside the GEM vulnerability tool that Victor showed you earlier. We, as you see links there to the exposure model. Once you have the different building classes, you want to produce a model of the building of a given class. The framework is quite flexible in that you could just use a single degree of freedom system to represent your structure, or you may have a full 3D model of your building. So there's various levels of complexity, modeling complexity in the framework. We have a database of all of those strong ground motion recordings from the engineering strong motion database are being used to develop the fragility functions, the vulnerability functions. So these include a lot of European records. And then a final sort of important part of the whole process is to do validation and sanity checks on the results that are coming out of the calculations. So to make sure that the estimates of damage and loss coming from these fragility and vulnerability functions make sense when compared with what's been observed in past events. So a few words on just the modelling part. So assuming I'm using a single degree of freedom system to represent my structure, I still have various ways that I can produce the capacity curve to describe the strength and the deformation capacity of that building class. So I could use, it's called type 1. Type 1 is simply a capacity curve that we take from existing studies. So this database of existing capacity curves, I may use that to produce the capacity curve for my building class under consideration. However, we're also developing tools and algorithms that will allow us to design the buildings as they were designed at the time of construction, so doing a simulated design of the building. So depending on what the code was at the time of that building class, depending on the lateral force coefficient that was applied at the time of design, we can simulate the design at the time, produce the capacity of this simulated prototype design structure, and do it from a pushover analysis. This slide that I skipped over was just to show that the existing capacity, fragility, and you can see there capacity curves, fragility, and vulnerability models that we collected will all be put into the GEM tool. So once you have a capacity curve, so let's say, for example, you're taking a capacity curve from experimental or the existing database to describe your building type, we will then have tools to do nonlinear dynamic analysis of that single degree of freedom system, which has that backbone capacity behavior. We use OpenSeas, which is an open source software where we can do nonlinear dynamic analysis. So our single degree of freedom system with a given capacity curve, we run it with hundreds of different recordings coming from that engineering strong motion database. And what we can plot then is for each recording where we run a nonlinear dynamic analysis, we have some measure of the intensity of that recording. It could be the peak ground acceleration, it could be the spectral acceleration at 0.1 seconds. That's what we're plotting here. And then we plot the response of the single degree of freedom system, the displacement response, for example. And then we do a regression analysis on this data, on this response data. And what we can then do is say, if we exceed different values of displacement, we will reach or exceed different damage states. So these horizontal lines you see here are displacements at which we may reach slight damage, moderate damage, extensive damage, or complete damage or collapse. And then from the statistics of this regression, which will tell us at a given level of ground shaking, what is the distribution of response, we can calculate the probability of exceeding these different levels of damage thresholds. And that's how we get our fragility functions here, seen on the right. Now, in terms of what do we put on the x-axis of these fragility functions, as I mentioned, we can have many different intensity measures. We could use peak ground velocity, peak ground acceleration, different spectral ordinates. We are developing the fragility functions in terms of spectral ordinates at periods of vibration close to the fundamental period of vibration of the building class. Because this is what the European ground motion model, the hazard, will provide us in terms of ground shaking. But we're also producing them in terms of a metric which is called average spectral acceleration. So the average spectral acceleration is the geometric mean of a number of spectral ordinates over a range of periods. And so for a number of different building classes, we define this range of periods and we calculate the average spectral acceleration. So we can plot all of the fragility functions using the same intensity measure. Because if I choose the spectral acceleration at the fundamental period, and these structures have different fundamental periods, then I can no longer compare the fragility functions because they each have a different intensity measure on the x-axis. But by using this average spectral acceleration metric, it's seen to be an efficient and sufficient ground intensity measure. We can plot them all together and do sanity checks. Do the results make sense? Do we have higher probabilities of exceeding collapse or extensive damage for buildings that we know are more fragile than others? So the adobe buildings, do they show a higher probability of damage as compared to the reinforced masonry, for example? So that's how we're developing fragility functions. As Vita mentioned earlier, vulnerability functions give us the probability of loss given an input ground shaking. To get from functions which tell us the probability of exceeding damage states to a loss, we need to use what we call damage loss models or consequence models. So when it comes to economic loss modelling, we're using a damage loss model that GEM has proposed from data that they've collected from across events, where they've looked at what was the cost of repairing different damage states from past earthquakes. So as you can imagine, the percentage of the total replacement cost of a building that needs to be spent to repair a slightly damaged building is a lot lower than the percentage of the cost of the total building that's needed to replace a completely damaged building or collapsed building. So that's what these ratios here are showing you. So a completely damaged building, one that cannot be used after the earthquake. Obviously the ratio of the cost of repair to cost of replacement is 1, or could even be higher to take into account demolition and other costs after the earthquake has occurred. And then there's obviously large uncertainty in these values, which also needs to be accounted for, these ratios, the coefficient of variation in the ratios. For fatality modelling, to go from damage to fatalities, we use the fragility functions which are for the complete damage, that last damage state. They tell us the probability of reaching or exceeding complete damage or near collapse. However, we know that loss of life is really related to collapse, the collapse of buildings. The complete damage state is a building that can no longer be used after an earthquake, but it hasn't necessarily collapsed, so will not necessarily cause a loss of life to people. So how do we get from that complete damage state to collapse? So we're using past earthquake damage data. In particular in Italy, there's been a significant effort to put together all of the collected damage data after earthquakes across Italy in this so-called Dado database. So in that database, we have both buildings that reach complete damage, and we can find out what percentage of those buildings that reach or exceed complete damage actually did collapse. So we can calculate this percentage of completely damaged buildings that actually collapse. And that's what we're showing here in this plot. This is for the Irpinia earthquake. We're also looking at how that ratio varies as a function of ground shaking intensity. Because you could imagine that a larger percentage of the complete damaged buildings actually collapse under higher levels of ground shaking than under lower levels of ground shaking. And so we're bringing in this empirical data to get a sense of the percentage of really fully collapsed buildings after an earthquake. Then once we have an idea of the percentage of the collapsed buildings, we then need to relate that to the fatalities, and that's where we use data that's been collected by a number of researchers, Emily So, for example, Robin Spence and Tonis Pomonis. So they're all working with us, sharing data that they've collected on the fatality ratios of past earthquakes. So the fatality ratio is the ratio of the number of fatalities to the number of occupants in the building at the time of the earthquake. This figure, which we can't read in detail, shows many, many different reinforced concrete buildings that have collapsed. I just zoom in and show you down the bottom here. What we're seeing is the reported number of occupants at the time of the earthquake. It's obviously quite difficult to know exactly how many people were in the building at the time of the earthquake, but it's something that can be estimated. And then the number of killed occupants, from which we can get a percentage of the total occupants that were actually killed and died in those buildings. So everything that I've presented here on the fragility and the vulnerability models, we still have a lot of work to do. We're still developing that framework, the tools, the algorithms, but we want to make everything available, again, through this European Seismic Risk Service. We would like to make the tools available so that you could also run and produce fragility functions using the same framework that we're using the OpenSeas software through what are called Jupyter Notebooks. Jupyter Notebooks use Python. They're quite easy to use, quite nice interface. You can add in your own capacity curve, for example, and run and produce fragility functions using the same method that we're using. So over the next year, this page on physical vulnerability on this website should start to have more tools for developing your own models, but also we will provide access to that GEM vulnerability database with all of the European existing models that we've collected. So bringing everything together for the calculation of physical seismic risk, we're using the OpenQuake engine. I'm not going to say too much about this because after my talk, Venetia is going to explain how we do the different calculations of physical seismic risk using the OpenQuake engine. But once we have outputs at the European scale, we will be sharing them through the European Seismic Risk Service website. We will have, for example, risk maps showing average annual losses, or maps showing losses for a given return period across Europe. We will have this country profile that Vita showed detail earlier, and as he mentioned on the GEM website, they plan to replace the country profiles across Europe with the outputs from the SERA project. What we would like to do would be to add also to this country profile some additional information, some additional indicators, which are the Sendai framework indicators. So let me just show you what they are. So we feel there are a number, not all of them, but a number of the Sendai framework for disaster risk reduction indicators can be readily calculated using the models that we're putting together. So we can calculate the number of deaths attributed to earthquakes per 100,000 population, the number of people whose damaged dwellings were attributed to earthquakes, the number of people whose destroyed dwellings were attributed to earthquakes, the direct economic loss to damaged or destroyed productive assets and not residential buildings, and to the housing sector. So all of these indicators will be added to that country profile. So that's really everything when it comes to physical risk. So the calculation of probability of damage or direct losses due to that damage following strong ground shaking from an earthquake. Within GEM's framework, they also bring in social vulnerability, recovery and resilience indicators. Vita showed earlier the figure which showed how hazard, exposure and vulnerability go into physical risk. Then social vulnerability, socioeconomic vulnerability is brought in to get a more holistic view of integrated risk. So this framework requires variables or indicators to be collected within the country for 3 different composite indices. So we are collecting within different administrative boundaries across Europe from census databases indicators that will allow us to estimate what is called a human lives index, an economic resilient index, and a recovery index. So these 3 composite indices, which are these 3 columns here, are the combination of a number of variables. So these variables, as I said, can be collected from existing statistics data in the country, and then they can be combined so that indicators that influence human lives could be access to hospital beds, number of hospital beds, population with formal education, and so on. So there's a number of indicators that have been identified from an extensive literature review to contribute to the impact on human lives after an earthquake. Then another one for economic resilience and recovery. Then once these indicators, or these composite indices, have been calculated for each administrative boundary across Europe, what we do is we combine it with the physical risk. So the first one, the Human Lives Index, is combined with the average annual loss of fatalities we calculate from our physical risk model. The second one can be combined with average annual loss in terms of economic loss, again from the physical risk model, and the third with the number of collapsed buildings. So we can produce maps like this one showed here, which are called impact maps, where we plot both the physical risk and these composite indices together. So we can see areas of the country where not just the physical risk is high because the hazard is high and there's a lot of exposure and some vulnerable building classes, but also it could be increased, aggravated by the fact that there's also a high social vulnerability in that region, and vice versa. Now those variables that I presented before on the table for those 3 indices, they're actually undergoing a lot of discussion. Are they appropriate? GEM has proposed a set of variables to be used at a global scale. We have a meeting next week in Pavia to discuss, are they appropriate for use in Europe? They may not be, but we will nevertheless demonstrate this process with the data we've collected. We will calculate the indices, we will produce these impact maps, but we feel that this is an area that requires a lot more local expertise and work to check, are these appropriate variables to describe the impact on those different composite indices. And then a final activity, which we will be doing a lot over the last 12 months of the project, will be to test and verify the fragility and vulnerability models and the full physical risk framework. So Vito already mentioned shake maps and how shake maps can be used to calculate losses from past events. So we will be doing that for events in Europe. So we're collecting loss and damage data from past European events. What we do is we take the shake map from that event. So that shake map tells us not just what the median ground shaking was over the region, but also what was the uncertainty in the ground shaking. So at some locations we know for sure what the level of ground shaking was because we had an instrument there, but in other locations a ground motion prediction equation has been used, so there's a high variability in the uncertainty in the level of ground shaking. So OpenQuake has a calculator called Scenario from Shake Map, where you can input your shake map, your median, and also your uncertainty, and it will then produce a large number of potential ground shaking fields that could have occurred during that earthquake. So here's one example of a random simulation of the ground shaking for that event. So we can produce 100, 200 of these different ground motion fields. Then given our exposure model for that region, given our vulnerability model, we put the components together to calculate the losses that are expected for this event. And we do that for all of the events that we have in our catalogue. And this is just an example showing, these are the results. So Vita showed you earlier the global results. These are the results just from Europe. So this is what the observed losses, which have been adjusted to today's value because we're using the exposure model from today, whereas the earthquake may have occurred 10, 15 years ago. So we adjust the losses to today, and we compare them with the estimated losses that come out of this calculator using the shake map, the exposure model, the vulnerability. And we're really checking that there isn't significant bias in our models. We will expect, obviously, quite large uncertainty, quite large variability in the results, but we want to make sure at least that we don't have a bias in the model. And so the losses come from various databases. Munich Re have a NatCat service where they have been collecting for a number of years the losses, the number of damaged buildings, the number of collapsed buildings, the number of fatalities from earthquakes since around 1980. There's also the NOAA Significant Earthquake Database, which is a public source of information. And so we're putting together these losses from these past events in Europe. Another way that we can test our models is against empirical models that have been developed at the European scale. So USGS, PAGER have developed empirical fatality models and economic loss models. So in black there, you see the PAGER model for Turkey for fatality vulnerability model. Now the PAGER model is actually in terms of macroseismic intensity, so we've had to convert that into peak ground acceleration using conversion equations, which allow us to go from macroseismic intensity to peak ground acceleration. Then we compare this vulnerability model for the whole country of Turkey that PAGER have proposed with our own model for Turkey. Now, our own model for Turkey has a number of different building classes, and each building class has its own vulnerability model. But if we calculate a national weighted average, considering the percentage of those different building classes in the exposure model, we can produce a weighted average vulnerability model for Turkey from our analytical fragility functions. And so we're just, again, these are sanity checks. These are checks to see how our models compare with empirical models from other groups, from other researchers. I should have mentioned, but the PAGER model, this black model, this has been produced using observed number of fatalities from past events. It's an empirical model. So we have 12 months left, maybe just under 12 months left before the end of the project. And our objective is to have a fully tested, complete European seismic risk model, which will be released in April next year on this European Seismic Risk Services platform I showed you. We will produce a preliminary version, however, this summer. We're covering 46 different countries in Europe, and so a preliminary version using a very first version of the update to the European Seismic Hazard Model, using the European exposure model that we currently have, hopefully improved following the next couple of days here at this workshop. Hopefully we can improve slightly that European model, at least within the Balkans region. So we're going to put those together to have the very first version of the European Seismic Risk Model for September, which we will be presenting at a workshop that is taking place at University of Boğaziçi in Istanbul on the 12th and 13th of September. So we've invited a wide range of people, and you're also welcome to come. We still have some spaces. If anyone here is interested to come, please let me know, and I will show you the registration form. But we have space for up to 100 participants from academia, but also from industry. We have people coming from the insurance and reinsurance industry, from cat modelling companies, from engineering companies, and we want to get feedback on this first version of the model through this workshop before we release the final version next year. In addition, we will be running an OpenQuake engine training course on the second day of that workshop. So you will get a brief insight into OpenQuake engine through Venetia's presentation that's coming up, but we will instead here in Istanbul spend a whole day going through with the users with their laptops how to actually run the calculations and reproduce the risk results that we have presented for you. So that's the end of my presentation. I think we're still quite good for time. But I don't know if any of you are on Twitter, but we're trying to get some people to follow us on Twitter. But also it's a good place because we will be updating you of when things are going onto the website, when models are being released, when first results are being released as well. Thank you very much.